Okay, so here we're looking at the second video on the notes quest. Okay, so here we've got the unit of energy section, and the first question is, let's say we write down 1A. What is a symbol for energy and work? Not the unit, so the symbol. So let's say if we're using an equation, these are classic equations, E equals mc squared. That's made up of the symbols for each of the quantities. So this is energy, mass, speed of light. And they have their own units, so mass will be kg. So the symbols for energy and work, well, the symbol for energy is E, and the symbol for work is W. There is another one, there's Q, which is thermal energy, but you don't need to know that. Okay, so at the moment it's just E and W. B, write a short paragraph describing what the SI, the System International Units, mean. Okay, well, effectively, when you write a science paper and it goes all the way around the world, it's a appalling map. Okay, so you got your countries around the world, it looks more like the moon. When people want to talk with each other and across different countries, you need to be able to talk in a common scientific language. So the SI units allow scientists, but not even just scientists, people, for example, in trade members, and so on, to talk in a common language. And this is a language of measurement, okay? I mean, it's very important if, let's say, you were in trade and you're selling a kg of wool to somebody in a different country, and they said, sorry, our kg is slightly different to yours, we think it's actually 900 grams, you might have a bit of a conflict around that, okay? So essentially, it just allows scientists to talk in a common language of measurement, okay? The system is governed by a society or a committee to make sure it is consistent. One day I'll get good at writing it on the computer. So, next step, we're going to copy this table. I'm going to do it actually on the table, makes it a lot easier. So the symbol for energy is E. Remember, you could also have W for work, which we'll look at later what work is. The SI unit is the joule, and we're going to put in a capital J there. Oh, actually, because I didn't do, this is actually 2A. Oh, that was appalling. And this is B. What is the unit? It's actually the joule. Force is F, and it's in newtons, and it's capital N. Mass is the lem, and it's the kilogram, kg. Time, small little t there, that's in the seconds, small s. Distance, we'll use d this year, and that is in meters, small m. Pressure, so it's P, and when you look at this one, we're going to be using Pascal, okay, and this is P with small a, so you need to look that one up. Voltage is V, and the same as EMF and potential difference, which we'll look at later. And so that's volts, essentially, V. And current is I, okay, just to confuse you, and that's in the ampere, and that has got a unit of capital A. And resistance, R, and it's measured in ohms, and omega is the symbol. Okay, so let's move that up a little bit. 3, state an energy value for each of the following situations below. You may need to ask the teacher or use Google. Not many people seem to ask me, but we'll have. So one example we have, it might not be a packet of food, but let's say we look at the Big Mac. Okay, so the Big Mac has on it, on the box these days, or even there's a little pamphlet you can get at McDonald's. I haven't actually been there for a long time, so I don't know, but you get a value in kilojoules, and it's about 2,300 kilojoules of energy. And about 1,000 of that is from the fat. Okay, so what you're going to do is just look on the back of a packet, and it will have product information, and then it will have energy, sugar, and so on. And the energy one should be usually done in kilojoules. There is a possibility it could be in calories, but generally these days the SI unit is joules, so it should be done in that. The energy is stored in the average car's petrol tank. Okay, so you guys might have a variation of the energy for the fuel, but let's say we have a common one might be 34.2 megajoules for every litre. Okay, so if you want a 50 litre tank, you just got to do that 50 times 34.2 megajoules. Okay. And you get around about 1700 megajoules. Okay, or without the mega there, that's 1700, but then you got to add on another 6 zeros of joules. So that's quite a bit of energy. Okay. In a petrol tank. The next one, C, the energy stored in a 1.5 volt AA cell. So that's your, or should we say battery there, sorry. So that is your normal AA battery. So having a look at this one. Okay, if you look it up, you usually get around about, let's say 2.5 to 4 watt hours. Okay, or you might have actually found the joule value, but if you found this one, this is actually an energy value, but it's got a size to it that we're going to do. Let's say we say four times a particular size. Now, what is a watt hour? It's effectively, if you have something that's going for 1 watt going for 1 hour, you're going to get a certain amount of energy, and that's actually equal to 3,600 joules. Okay, so it's just going to be 4 times 3,600 joules. And so you would use your calculator and get 14,400 joules. Okay, what we're going to do next, I might move this even further out of the way. If I was smart, I should have shrunk it down. Oh, no, let's move it up there. And we're going to grab this one and expand that a bit. Oh, straighten it. Okay, so this one here, D, I. The energy stored by a 1000 kg car going 10 meters per second. Now, the actual formula we're going to use is this one here. So EK, your energy that you have, is so this is kinetic energy, is equal to half mv squared. So 0.5 times your mass, which is 1000, times your speed, 10 squared. So we'll show you how to do that in the calculator. So you got 0.5 times 1000, 1000 times 10, 10. My pen keeps touching it. 10 squared. Okay, and that equals 50,000. Okay, so the next one, II. the kinetic energy of a truck going 2 meters per second. So a truck, let's say a truck mass might be around about 3 tons. So let's say 3,000 kilograms. So then we put it in, EK equals half mv squared. And that was going to equal to half times 3,000 times 2 squared. So 0.5 times 3,000 times 2 squared. You get 6,000 joules. So you notice the speed makes more of a difference. So the speed makes more of a difference than the mass, really. Okay. 4. Find out how much energy it requires to lift a 1 kg mass to 10 centimeters. Calculate it and state it using energy equals weight times height, where weight is equal to mass times gravity. So let's do the weight equals mass times gravity first. So our mass is 1, and we're going to multiply it by gravity, which is 10. So gravity is 10. And that will give you what we call 10 newtons. Weight is a force. We look at weight more later. B. Oh, sorry, I haven't finished yet. We need to then find out what the energy is. And we call it potential energy. And it's going to be weight times height. So my weight is 10 times the height. Now the height needs to be in meters. And we get 0.1, so we get 1 joule. Conveniently, I chose that. Describe how this compares to the energy of the food packet you found earlier. So let's say we look at the Big Mac. So remember the Big Mac is equal to 2,300 kilojoules. So if you divide that by 1, you find that the Big Mac is 2.3 million times the energy. C. How many times must you lift this mass of 1 kg to equal the same amount of energy as in the food packet? Show it working. Well, I'll just show you. So we get 1 joule is 1 lift. Okay. So how many of these lifts do you need to get to 2.3 million? Well, you need 2.3 million. I'll write it the other way. You need 2.3 million times. That is a lot.